Seems people are still joining. We'll start at 3:05. Okay, I'll begin now. So welcome everyone. I'm Anand. And this course is on electromagnetic simulation using the FDTD method. So I'll keep my camera on for a few more minutes so that you get familiarized with who is taking the course. And to save bandwidth, I'll turn it off. Uh, so um, So this course is being offered by ISSS. I hope everyone has registered, and whoever has not yet registered, please put an email to me. I'll get back to you with the details which I need for the registration. And whoever, I guess everyone has already received a login ID and password for their ISSS portal. And if you have not, please remind me. Put an email. So about me, I'm Anand. I'm a Prime Minister's Research Fellow at the Indian Institute of Science. I work in the Department of Electrical Communication Engineering, and my PhD advisor is Professor Devdeep Sarkar. Um, Regarding my education, I did my bachelor's from Indian Institute of Technology, Dhanbad, in Electronics and Communication Engineering, and I'm a direct PhD student over here. This is my third year, and my area of specialization and interest lies in space-time varying metamaterials, computational electromagnetics using finite difference time domain technique, MIMO antennas, and radar systems. Uh, since some of you or most of you might be not familiar with the interface of Teams. Uh, on the top right side of your screen, on the corner, you will find this particular interface where you'll see these options where you'll find the option for chat. So there is an option for reactions where you can raise your hand. You can see in the screen I have raised my hand, and you can see that I will be able to see who has raised. And if you have any questions, please raise your hand. And if your question get answered, please use the same button to put your hand down. Uh, So, like for a show, if you're getting this, can you please try try this reaction and raise your hand? I'll know that I'm being like it is being communicated. Yeah, I can see you are able to raise your hand. Okay. Uh, Thank you. To save the bandwidth, I'll turn off my camera. I hope everyone is familiar with my face now. Okay. So we'll move to the next slide. So beginning with why should we use computational EM simulation, or why should we know it? So the actual solution to the Maxwell's equation is very complex for realistic problems. Like for simpler, when you have an object with a very simple geometry, you can probably solve it analytically. But for realistic problems, there will be a lot of corners. The structure will be complex. It might have a lot of components to it, different materials, and approximations are usually required. Uh, and to deal with it, we use computational EM simulations. There are various solvers available in the market, HFSS from ANSYS, CST by the Salt Systems, COMSOL, Numerical, and whatnot. So now the applications of CEM are huge. So it is used by antenna designers to study of biological effects in medical sciences for diagnosis and treatment, for microwave devices, MMIC circuits, for environmental issues, surveillance and intelligence gathering, radar imaging. There are a lot of applications for this for the study of computational EM. Now, like how do we approach a problem? So it can be there are various ways you can approach solving a problem. First, beginning with Maxwell's equations. I hope everyone is familiar with the Maxwell's equation. I see two hands are raised. Do you have any questions, Akash, Sudev? If if yes, you can unmute yourself. If no, then maybe you can put your hands down. Okay, I guess no questions. So, solving an EM problem, using computational electromagnetics, you can you start with the Maxwell's equations. Now, Maxwell's equations can have two forms, which can be either it is written in the integral form or the differential form. So, beginning with them, and you can solve it in the frequency domain or in time domain. Now, depending upon what your problem is, you choose a method. Either use integral equations or use differential equations and solve it either in frequency domain or in time domain. And your problem could be 1D, 2D, 3D, and 2.5D, for example, in case of PCBs. And you choose a method and solve it. So, for example, popular methods are like EFI, MFI are full wave solution in frequency domain using integral equations. Similarly, FDTD is a full wave method. It can be used for 1D, 2D, and 3D problems, and it uses partial differential equations, and we solve the problem in time domain. Another popular solver, ANSYS HFSS, popular among the antenna designers, it is also based on partial differential equations, but HFSS solves the problem in frequency domain. Now, why this course? So you want to get started with computational electromagnetics, and you're looking forward with finite difference time domain method. You already know CM techniques, and you want to get started with FDTD in particular. Or you already know FDTD and you might want to go through this course to revise up or brush up on the like theory, and you want to understand the working of EM simulators. So a lot of us already use many EM simulators, and an understanding of how the simulator works, you might be able to better exploit its advantages. Like if you know how a simulator works, you might be able to use it more judiciously. uh, for BTech and MTech students, in particular, from this course, you will be guided to developing your own simulators, and I'm sure you will be able to do an amazing project if you like go through this course. Now, starting let's take a poll on how many of you are already familiar with the technique. So I hope you will get a poll on your screen, your question. So I hope everyone has received a notification, and like I would like to know how many of you are already familiar with any CM method. Might be FEM, MOM, FDTD. Um, so a lot of you, like half of you, are already familiar with some of the other techniques. That's nice to know. It will be easier for you to follow. And those who have, like half of you have not yet like used any, are not familiar with any CM method. Don't worry. We'll go through it in great detail. Today's class is basically brushing up on the basics of EM theory. Today we won't be discussing any FDTD. We'll go through the basics. Today the class might be also short. This is more of an introductory session so that you get familiar with the interface, the course, the requirements, the logistics. So I've received 22 responses out of 31, and I can see 55% of you have answered yes. So that's great. And for the rest 45%, I'm sure you will be with me with till the end of this course. Okay, so we'll move toward things. So at the end of this course, what am I offering? So you will at the end of this course you will be able to follow literature on the finite difference time domain method. You take up any paper, you will be able to follow most of it. You will know the working of EM simulators, mostly the simulators which use finite difference time domain method in the background. You will be able to write your own 1D, 2D, 3D FDTD codes. You will be able to perform EM simulations of wave propagation and their interaction with the different media. You will be able to include objects, obstacles, the obstacles with different material properties. So we'll uh, pause for a second and take up any questions if you have. You can raise your hand and ask, and then unmute yourself and ask. Okay. So no questions. We'll move forward. Now the outline of this course. So we'll start with the review of EM theory. We'll go through Maxwell's equations, the constitutive relations, the boundary conditions. Then from the next class, we'll start with the one-dimensional formulation for the FDTD method. We'll go through different stages, all the requirements of that we should know with before we start writing the code. We'll almost take uh, two lectures, approximately 4 hours on the second module. The third module, uh, okay, there's a question from Anjali. Anjali, yes, you can unmute yourself and ask the question.
So we'll be doing coding in MATLAB.
Yes, yes. Sorry. Okay. I'll put a poll right now to know how many of you are already familiar with MATLAB. Okay. So let's see how many of you are familiar with MATLAB. So this, so you must see a poll again. Um, because so far everybody is like either familiar or somewhat familiar. So to answer your question, Anjali, yes, we'll be using MATLAB, but the formulations developed over here can be used in any language. Like the textbook which I'll be following by Sullivan has sample codes in C++ or C, and the same a similar book is available from him for Python. And this in this particular course, I'll be using MATLAB because implementing codes in MATLAB is much more easier running it, and like plots and stuff which I need for this particular course. The MATLAB generates very beautiful plots, so I'll be using that. So
Okay.
almost all of you have answered yes, and some of you have answered somewhat. So I guess everybody is familiar with MATLAB. Anjali, any follow up questions? No. So there's a question in chat. Will you be sharing the slides later or any of the material? Yes. So I hope everyone has received an email from ISSS with your login ID and password. Over there on that portal, I'll be uploading the lecture recordings and the slides and all the materials required for you. Even a few assignments will be uploaded. Tazeen, I guess I have answered your question. Any follow-up questions? Oh, okay. Okay, so if you have not yet received the login ID and password, please for sure drop an email to me. I'll contact the Triple S admin. Okay, so in the third module, we'll look up for on more topics on one-dimensional simulation. We'll look at the frequency dependent media and generating the frequency domain output. Since FDTD is time domain method, uh, ex, uh, extracting frequency domain output will use FFT from MATLAB. So then we'll move towards the two-dimensional simulations. We'll look at the different things required for two-dimensional simulation. Mostly, it is an extrapolation of one-dimensional problems, and we'll look at the perfectly matched layer, which is necessary to perform EM simulations in using FDTD. And then finally, we'll look at some problems in 3D. So today's lecture is all about review of EM theory. I know most of you are already familiar with the EM theory basics. I'll just run with the top different topics that we should know in the back of our head that which will be required for this particular course. I won't be stressing on any problems. I'll just go through the different topics. So another important information, these are the four textbooks which I'll be following for this course. So for the review of EM theory, I think the book by D.K. Cheng, Field Wave and Electromagnetics is the best. You can also look up for the book by Professor Balanis. That is also a very good book. For this particular lecture, the slides have been prepared from the book by Matthew and Sadiku. If you want to refer to the material from this lecture, you can refer to the chapter one from this particular book. And the rest of the for the rest of the lectures, I'll be referring to the book by D.M. Sullivan and David B. Davidson. These two books are on finite difference time domain method. Other about this class, so the timings are 3 to 5 p.m. on Saturdays and Sundays. I know this particular month will be the weekends are holidays, the New Year and Christmas. So we'll adjust accordingly. I'll any information I'll email and post on the IEEE portal if we reschedule classes. So I put the meeting link over here, the course website on the IEEE webs, IEEE portal. The my contact email is over here. I am sure everybody already has it. And for this course, I will be giving take home assignments. The solutions I'll share in time, and I encourage self evaluation. If you have any doubts, please feel free to reach out to me. Okay, so we'll again pause and take up any questions if you have. Yeah, thanks, Bhargavi. I forgot to mention for the approximate number of hours this course will be around 16 hours, hopefully, maybe less. I'm aiming to finish this course by the mid of January. I hope that answers your question. So I'll go back again to the course module. Okay, so today's class is on review of EM theory, and the next two classes will be on one-dimensional simulation FDTD method. Another one class on more on 1D methods. Two classes, approximately 2 to 3 classes on 2D simulation, and maybe two classes or one class on the 3D. I'll touch upon the topics how to implement 3D. Any other question regarding the course logistics? Okay, then we'll begin with the slides. Okay, so we'll start today's lecture. So these are the two books which are like the basics of this slide. We'll look up at the electrostatic fields, magnetostatic fields, time varying fields, Maxwell's equations, boundary conditions, wave equations, time varying potentials, time harmonic fields. So I guess all of you are already familiar with this, since all of you are from the electrical engineering background. But again, for the like to for the completion of this course, like for the fullness, I'll be going through the different topics, so that you know what to study before we start with the FDTD. So two important theorems used in the EM theory are the Gauss's divergence theorem and the Stokes theorem. So I'm sure everyone is familiar with it. So EM theory can be regarded as the study of fields produced by electric charges at rest or in motion. So if they are at rest, we get the electrostatic fields, and if the charges are moving with uniform velocity, we get the magnetostatic fields. So if these charges are accelerated or there are time varying currents, we what we achieve is the time varying fields. Now, important laws for the study of electrostatic fields are the Gauss's law. Its differential form is given by the divergence of electric displacement d equals rho, and the electrostatic the law describing the electrostatic fields as conservative. That is the curl of E equals 0. So D over here, the notations I'll be using will be the bold D is the characters in bold are vectors. So D is the electric flux density, E is the electric field intensity, and the electric flux density and electric field intensity are related by the expression D equals epsilon times C, where epsilon is the dielectric permittivity of the medium. Now, we can also express the electric field intensity in terms of electric vector potential. It is given by negative gradient of electric potential V. Now, combining these equations, that is the divergence of D and T in terms of electric field E, and the electric field in terms of electric potential, we get the Poisson's equations. So if you can for if you and in case you have in doubt, we can connect and discuss. So you get the Poisson's equation for constant epsilon. And so this is the very popular form of the Poisson's equation, and for rho equals 0, this particular equation transforms to what we known as Laplace's equation. Now, for magnetostatic fields, similarly, we have the laws, Ampere's law, and its differential form is given by the curl of magnetic field intensity equals JE, where JE is the current density. Uh, the law of conservation of magnetic flux, also known as the Gauss's law of magnetostatics, and its differential form is given by the divergence of magnetic flux density equals is 0, and the magnetic field intensity and magnetic flux density are related by the expression V equals mu times H, where mu is the permeability of the medium. Now we can express the current density in terms of the electric field by this point form of Ohm's law, where they are related by J is equals to sigma times E, where sigma is the conductivity of the medium. And we also have the magnetic vector potential represented by A, and it is given by the and the magnetic flux density is expressed as the curl of A. Now, using the this vector identity, and the Coulomb's gauge condition, which is given by the divergence of A equals 0, we get the Poisson's equation for the magnetostatic fields, which is given by del square A equals minus mu times JE. And when JE becomes 0, we get the Laplace's equation for the magnetostatic field. Now the time varying fields, the time varying EM fields are expressed mathematically by the Maxwell's equations. We have 4 Maxwell's equations, which are given by the curl and divergence of magnetic flux density, electric flux density, and electric field intensity and magnetic field intensity. So I hope everyone is familiar with these Maxwell's equations. So we won't spend much time. So, as discussed in the beginning of this lecture, so Maxwell's equations can be expressed in either differential form or the integral form, and the different for different medias, the 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 field and the magnetic the field and the flux density are related by the constitutive relations. Now, for the boundary conditions, so E, so for, let's look at these important terms. So throughout this course, I'll be using terms like linear, homogeneous, and isotropic media. Now, what are those? So a medium is linear if their constitutive parameters, which are conductivity, permittivity, and permeability, if they are independent of the electric field and magnetic field, they are said to be linear. For a homogeneous medium, if these constitutive parameters are not functions of space, they are said to be homogeneous, and if they are functions of space, they are said to be inhomogeneous. For what do we have in isotropic media? So if the sigma, epsilon, and mu, the constitutive parameters are independent of the direction of the media. So if the epsilon or mu changes is different for different directions, and then the medium is said to be anisotropic. And if they are same for all the directions, they are said to be isotropic. Now, the boundary conditions for the electric field and magnetic field at the interface are given by the set of equations. These are so for the tangent, so that we know that the tangential fields are same, and similarly the normal fields are given by this set of equations. So we will not spend much time on this. So this lecture will be very short, and I hope everyone will refer to the textbook if you have any doubts. Oh, there's a hand over here. Yes, Manoj, you have an. Please unmute yourself and ask the question. Manoj, if you you have to unmute yourself to ask, or you can leave your question in chat if you are unable to unmute yourself. Okay. Yeah, discussing about the boundary conditions. So the so basically when the fields the waves move from one media to another. So what we okay. So it's the same question on boundary conditions. So so the boundary so when fields move from one media to another, we have to check the continuity of the Maxwell's equations. So so these particular set of equations will help us uh, solving the field equations on the boundary. So the subscripts T refer to the tangential fields, and the subscripts N refer to the normal fields. So we so when we say E1 T equals to E2 T, we mean that the electric field in the medium one, the tangential field in the of tangential electric field in the medium one will be equal to the tangential field of the tangential electric field in the medium 2. Similarly, the uh, the tangential field and the tangential magnetic field in the medium 1 is related to the tangential field in the tangential magnetic field in the region 2 by the second expression, which is equals to k. So k is the uh, so the k is the current flowing on the on this particular boundary. Similarly, for the electric flux density, the normal component of the electric flux density in the medium 1 will be is related to the normal component of electric flux density in the medium 2 by the third relation, where rho s is the charge on this boundary, is equal to the charges on the boundary, and the magnetic flux density of the medium 1 is related to the magnetic flux density in the medium 2. So they are equal on the magnetic fields are equal. I hope like I was able to give the gist of what these particular equations mean. Okay, so we'll move forward for the now the wave equations. So the time dependent vector Helmholtz equation, or simply the wave equations for a linear isotropic homogeneous source free medium is given by this particular set of equations. Now, if the if the medium properties changes, then the mu and epsilon will change, and accordingly the equations get modified. And if there is source, the this equations will be equal, the right hand side won't be equal to 0. So for a simple source wave medium, we have this set of equations, Helmholtz equations, known as the wave equations. Now, a good exercise for you will be to use the Maxwell's equations to achieve this result. It will brush up all the topics covered till now, and you might find this vector identity helpful for getting the results. Now, for the time varying potentials, although we are interested in electric and magnetic field intensities, which are physically measurable quantities, but solving using E and H might be like a little complex. Therefore, we use the auxiliary functions for analyzing the EM fields. And what are these auxiliary functions? These are none other than the scalar electric potential, denoted by V, and the vector magnetic potential denoted by A. So the derivation of V and A are based on these two fundamental vector identities, where the curl of gradient of uh, phi, which is an arbitrary scalar field, equals 0, and the uh, divergence of curl of vector field F equals 0. So we'll start with the Maxwell's equations. Taking up the second Maxwell's equation, we see that the divergence of vector field B equals 0. The comparing it with the divergence of curl of vector field F equals 0, we can express we can define A such that B equals curl of A equals 0. B equals curl of A. Now, similarly, uh, uh, taking the third Maxwell equation and substituting the B equals curl of A, we and comparing it with the other law, vector law, we see that uh, we define E plus del A by del T equals negative gradient of V. So and rearranging it, so we can express the electric field E in terms of electric scalar potential and magnetic vector potential. And we have already expressed magnetic flux density in terms of magnetic vector potential. So if we knew the potential functions V and A, the field E and B could be obtained using this set of equations. However, we still need to find the solution for this for V and A. Okay, so starting with the two equations that we derived in the previous slide. Over here, we are assuming linear and homogeneous medium because if the medium is non-linear, more differential terms will appear, and mu and epsilon will have to use the they will be included in the differential forms. So taking the curl of A, we get this. We will get this particular equation. Now, this equation might seem very daunting. We don't have to worry about it. Uh, Now, so we have used this particular identity to achieve this particular equation, and from this, furthermore simplifications, we will get this equation. We don't have to worry much about this particular equation. Uh, okay, now looking at the divergence of E from the Maxwell's equation is given by rho by epsilon. And over here, so if we put the divergence of E over here from this particular equation, we can will and comparing the both the equations, we can write this particular wave equation, this particular equation in terms of V and A. So we have completely eliminated E and B and all the electric and magnetic field terms. Don't have to worry about these. These equations might seem very complex, but you don't have to worry about. They'll get simpler in the next slide. So according to the Helmholtz theorem of vector analysis, a vector is uniquely defined if and only if both its curl and divergence are specified. Now we had the curl of A defined earlier, and so we may choose divergence of A such that these differential equations become very simple. So in the previous slide, as you just saw that these two particular set of equations we had derived. Now they are very complex, but choosing a simple by from the Lorentz gauge condition from the Lorentz condition, we can simplify this particular both the equations. So the Lorentz condition is given by divergence of A equals mu epsilon times dV by dt. So this is the Lorentz condition, and using this, so we had the curl of A, and now we have the divergence of A. So A is completely defined, and using this particular condition, we get this particular set of equations given in this box. So both these equations have become very simple, and you can see these are nothing but the wave equations in terms of magnetic vector potential and electric scalar potential. Now, the solution to wave equation is a very standard process. We don't have to think much about it. We just plug in the variables and get the answers. And now, and the integral solution to the equations are called the retarded potential. We don't have to worry much about this particular derivation a lot, because we are just going through it. So to brush up the EM theory, for this particular course, we will start with the Maxwell's equations and their 1D and 2D wave equations. But the derivation of the vector potentials is very important in methods using frequency domain techniques. Now, for the time harmonic fields, we are familiar with the word phasor. So we use phasor to simplify. We use phasor notation to simplify the writing of the vector fields. So for a time dependent field f, we can write f rt in terms of, in its real form, and the frequency component is given by the e power j omega t, and from so you only need to focus over here. So for any time dependent field, we will be expressing using this particular expression. And similarly, for all the required electric field and magnetic fields, we can express them in this particular form. Now, once we have written the electric fields and magnetic fields in terms of their phasor, we can simply simplify the Maxwell's equations, all the differential terms in the Maxwell's equation. We know that e power j omega, the derivative of e power j omega t can be simply written as j omega t, j omega e power j omega t. So if we plug in this thing in the Maxwell's equations, what we get is the Maxwell's equation in the frequency domain form. So, but for this course, we'll be using the Maxwell's equation in their time domain form. Yeah. So this particular lecture, we went through very quickly through these electrostatic fields, magnetostatic fields, and all the topics. So if you have any questions regarding the material, I would recommend you to go through the textbooks so that you can read yourself, and if any questions arise, you can reach out to me. So this was only the basics. And we'll begin with the FDTD part from the next class. Tomorrow we'll be having our next class from 3 to 5. So we'll start with FDTD tomorrow. So if you have any questions, you can maybe raise your hand and we can discuss.
So you will be doing the coding in MATLAB, like you will be showing us the coding part, or you will just cover it in theoretical mode only.
Both. I'll be uh, first. I'll be going through the derivations and formulation. How we like how we get the equations for coding in MATLAB. Like you start with the differential form of Maxwell's equations, and we'll use the central difference technique to rewrite the differential equations in the central difference form, and then we'll use the central difference form to write codes in MATLAB. Uh, I'll also show codes. I'll also run codes with you. You don't have to worry about it. The coding part is essential to this course. So I'll be teaching how to write the equations in MATLAB as well.
Okay, sir.
Yeah, yes, Ankit. You can unmute yourself and ask the question.
I think Anand, I just think it was a very nice lecture. I love the way that you teach us. So I just want to appreciate your effort. That's why I raised the hand. That's all.
Thank you, Ankit. I'm sorry. I think I rushed a lot in this particular lecture, but since this course is very particularly focused on FDD, I just wanted to. These topics explanation will take a lot of time if I go through one by one. But I wanted to show which topics will be important and which should know. So I'm sorry if I rushed a lot, but I'll recommend you please go through textbooks, the basic EM theory textbooks. All the material covered over here is what has already been taught at an undergraduate level in the beginning of first second year, I guess. So if you have any questions other than this particular material shown over here, you can ask now as well. And thank you, Ankit, for this means a lot.
Thank you.
Any follow-up questions, Ankit? I can see your hand raised still.
No, not at all. I don't think why it's showing. I just want to stop it. Does it?
Okay,
No,
you can
no.
go to the reactions and again click on the hand button. Yeah.
Okay.
Any questions? Anyone else? If you can unmute yourself and ask.
Anand, I have also one question. If you don't mind, I can ask.
Yes, sure.
Hello. Uh,
Yes.
uh,
Mm.
so the whole course is for implementing boundary conditions, or how further we go through the course, or it's
Okay.
dependent on the time.
So I'll go back to the course outline so that I can explain it more clearly. Yes. So I hope this is still visible, the screen.
Yeah.
Okay, so today we just went through the review. tomorrow's class will cover the FDTD equation formulation. Uh, we'll discuss a little about the partial differential equations, and then we'll start with the FDTD equation. Start with the Maxwell's equation to form the FDTD equations. We'll discuss the stability. We'll discuss the absorbing boundary condition in tomorrow's class. I'll show some examples of what we can achieve. But tomorrow's class won't we won't have much coding. We'll go through the analysis, the analytical part, and the next class I'll discuss the propagation in different electric medium, using different sources, because using just a sinusoidal source or a Gaussian source might not suffice. So we'll discuss a few sources. We'll discuss on the cell size and the medium, and then after this we'll have a special session, like a time dedicated to running the FDTD code. Like I'll show you an example of a code, and we'll go line by line in that code, like how has that been implemented. And then again we'll move towards the obtaining frequency domain results, and using simulating frequency dependent media, and then again we'll go through the code. Similarly, we'll move forward towards the 2D and 3D simulations.
Okay, thank you.
I see one another hand has been raised. Or do we have any questions in chat or no?
Yeah, hello.
Yes,
Sir.
Vivek,
So
you can unmute yourself.
I just want
Yes.
to ask whether you will cover any simulation tool as well in this course.
Come again. I think I lost you for a second.
Sir, I just want to ask whether you will cover any simulation tool in this course, like ANSYS, HFSS, or something else.
No, in this particular course, we won't be using any commercial tools other than MATLAB. We'll write our own codes to simulate the propagation of EM waves, and then we'll add a few objects and see go about it. So no, we won't be using any solvers over here. We'll write our own codes. That is the fun part over here in this course.
Okay, sir, got it. Okay, thanks.
Yeah. Yes, the class. There's a question in chat. The class recordings will provided to later. Yes. So I'm also new to the IEEE portal. So in the next class I'll add a few slides on how to access the slides. But yes, I'll figure out how to share the recordings on the portal. I think most of you have already logged in and on that portal. If not, please check your spam or inbox. You will have the I think you should have received the login ID and details over there. You will be able to. I'll still need to figure out how to upload the lectures over there. But yes, I'll be providing the class recordings. There's another question. Is the joining link will be the same tomorrow as one? Yes. So this particular link will be used throughout the for all the classes in this course, and for your registration. Yes, Priyank. You can say okay. Please drop an email after the class so that I don't forget. I'll ask for your details which are needed for the registration, and I'll forward it to the IEEE admin. Regarding the slides will also be available on the same portal. Any more questions? We have a lot of time actually, but today we'll end early. Maybe from next class we'll spend more time on the material. Seems like I've answered all questions. Okay, we'll wait for a few more minutes so that if you have any questions you can ask. Meanwhile, I'll stop the recording.